So hi guys, today I'm going to explain to you what is a binary search tree. So binary search tree is a tree where each node of it has a comparable key, which we can also understand that each node of it has a assigned value. And also this type of search tree is also called as sorted or ordered search tree. I'm going to show you later on my answer on number 1. So hi guys, this is my representation on how I answered the question number 1. So basically, before I'm going to show you the answer, keep in mind that we're going to follow the algorithm of the BST, which is we're going to visit first the left subroot, take the value of the node, and after that is we're going to visit the right subroot after taking the node. So without further ado, I'm going to explain you first why there's such LNR above for each nodes to its subroots until to its leaves. It's because this algorithm should be applied and restrictedly followed up by each value to the to what you are saying to the binary tree. So let's start. So as you can see, I've made 200 as the top node, and keep in mind following the algorithm, which is we're going to first go to the left subroot. Yeah, so here it's still so in order for us to never get lost to what we are doing, we're going to put a scratch on that. And same here, because 100 still wants us to go to the left subroot, same to 40 and to 20. Why? Because still, even though 20 doesn't have a left subroot, neither a subroot, which we had confirmed manually and obviously, so since we have nothing here to check and to go further, we're going to take the value of 20 and put out in the output, which is going to be here. So next is, since we're done here, we're going to go back to where we came from. Since we have done checking the 20, we have to erase the 40 of the left subroot of 40. So now, since we have done checking that, we're going to take the value of 40 since n was left in the above of 40. Put it below 220s and delete n. So now, applying the same algorithm, we're going to check for its subroot, because it's what tells us what to do. And since there is, following the same algorithm, there's no left subroot, neither right subroot, we're going to take the value and deleting the LNR of 80. So now that we have checked the right sub 3 of 40, we're going to delete the R of it. Now going back to 100, we're going to delete L because we have checked the the left subtree of 100 and taking the value of 100. And after that, we're going to check its right sub 3. So 120 has still wants us to check the left subtree and it doesn't have one. Erase it. Copy the node 120, then erase them both because we have confirmed obviously that 120 has a right subroot, which is 150, and still it doesn't have any left neither right sub 3. So we're gonna delete the LNR of 150. So because we are done checking that one, and to make it clear for us that these nodes here or roots here are done checking and gathered their outputs. Now since we have done checking here, we are going to go back here, back to here, and back to here, because we have confirmed that this part here is done. So deleting the L of 200, copying the value of 200, then deleting n as well as r, because after copying the node, as what I've said, following the algorithm, we're going to the right subtree of 200. So still applying the same algorithm, we're going to the left subtree and going to the 275 left subtree and 250. So 250 still doesn't have a left neither right subtree. Deleting LNR, take the value here to 250. So going back to 275 because we have confirmed 250 doesn't have anything much to do. We're going to delete L and N and R because we are done here. We have checked that 275 doesn't have a right subtree. Copy that 275 down to 250, then going back to 300, deleting L, then N because we are done checking here, and taking the value of 300. So after that, we're going to apply the R of 300, which is we're going to the right subtree of 300, which is 350, and still applying the LNR above of it. We're going to check if there doesn't, deleting it and getting the value below 300, which is 350, and check deleting R because we're going to apply it now, which is left. The only value left is 400, and since it's the only thing that we're going last, we're going to delete it entirely because we are now done. So 350, below it is 400. So now that we are done, if we think as computer algorithm, it's going to go back to 200 because it's kind of had done its job. And notice the output, the 20 is ascending from rising to 400, right? That's why BST is kinda called sorted or ordered type of binary search tree. So I think that's it. Thank you for listening.